Hello dear students, welcome to Pen and Paper Chemistry on YouTube, and we will continue our learning about the topic of aldehydes and ketones. This is part 7 of the videos on the properties of aldehydes and ketones, and as usual my favorite request is for you to quickly grab your pen and notebook so that you can take down notes for offline reference. So let's get started. In the previous video, we spoke about aldol or ketol condensation, and we've done the mechanism also in greater detail. Now this was the reaction of aldehydes and ketones with dilute alkalis, and it was a reaction which was shown by aldehydes and ketones which contain an alpha hydrogen atom. Today we are going to talk about Cannizaro's reaction, specifically shown by aldehydes and ketones which do not contain an alpha hydrogen atom, and this reaction takes place in the presence of concentrated alkalis, somewhere to the tune of around 50% concentrated sodium hydroxide or potassium hydroxide. An interesting point to note, this is an example of disproportionation reaction. Oh my god, lot of information right on one slide. So let us break it down into smaller points. I hope you are all noting it down because you won't have access to YouTube during your examinations, right? In the previous video, I have already explained to you the concept of alpha hydrogen atom. Again, going back to what we did, if this is our functional group carbon, so CHO, the carbon next to it is known as the alpha carbon, 2 next to it is beta carbon, 3 next to it is gamma carbon, and respectively the hydrogen atoms attached to it. So the hydrogen attached to alpha carbon is an alpha hydrogen atom, beta hydrogen atom, gamma hydrogen atom. In the case of ketones, you have alpha carbon atoms on both sides, as in this example that I have taken. You have 2 beta carbons. So effectively you have 4 alpha hydrogen atoms. Cannizaro's reaction is shown by only those aldehydes which do not have an alpha hydrogen atom. So here our simplest example would be HCH double bond O, which in the IUPAC system would be called as methanol, and which is also commonly known as formaldehyde, right? Now, aldehydes which do not have alpha hydrogen atom react in the presence of 50% concentrated alkali solution to convert into an alcohol and a carboxylic acid. But because of the presence of the alkali, the carboxylic acid turns into its respective salt. So if I am using NaOH, then in that case the salt that will be formed is HCOONA. So first step over here, let us break it down. HCHO plus NaOH, let me put it as the simplest alcohol. Now from here, the alcohol that will be formed, the corresponding alcohol that is formed is methanol with 1 carbon atom, right? Then it forms the carboxylic acid. The corresponding carboxylic acid is HCOOH. But as I explained just now, the acid reacts with the base and we will have the corresponding sodium salt of the carboxylic acid. So you will find that in the equation we actually write directly as the sodium or the potassium salt. So HCOONA. We've got an aldehyde with 1 carbon atom. It is converting itself to an alcohol with the same number of carbon atoms and an acid containing the same number of, that is 1 carbon here in the acid and 1 carbon in the alcohol. So if I were to balance this equation, right, now give me how many HCHO molecules will be involved over here. Try and balance this equation. Have you done it? Look carefully. You've got one carbon atom on the left hand side, but you've got two carbon atoms on the right hand side. So if I were to balance this equation, I'd put a 2 over here. Now let's check the hydrogen. 1, 2, 2 times 2, 4 and 1, 5 hydrogen. Look at this over here. How many? 3 plus 1, 4 and 1, 5. Sodium 1 on the right hand side, sodium 1 on the left hand side. What about oxygen? 2 times 1, 2 plus 1, 3 oxygen on the left hand side and 1, 2, 3 oxygen on the right hand side. In other words, in this reaction, 2 molecules of methanol are getting involved. One converting to alcohol and one converting to carboxylic acid with the same number of carbon atoms. The number of carbon atoms is not increasing in each of the products which are formed. Would you like to give the second reaction a try? If you see over here again, benzaldehyde plus NaOH. Our benzaldehyde does not have alpha hydrogen atoms. So what will be the product formed? Be very, very careful about where you are going to put the OH and how you're going to get the carboxylic acid. Okay, how many of you have written this product? By the way, don't forget to mention that we are using concentrated alkali over here. Instead of NaOH, we could also use KOH in both the cases. Let's get back to our equation. So, have you written the product as C6H5OH? So, C6H5OH and C6H5COONA. Have you written the product like this? If yes, then the first product of yours is wrong. Can you think about the reason why it is so? Look at what I told you in the previous reaction. The number of carbon atoms has to remain same. It's the CHO group which is getting reduced to an alcohol and it is getting oxidized into a carboxylic acid. So try forming this product once again. I can easily give you the answer, but I want you to understand it yourself also over here. Okay, so let us form the product here. You see, again, our benzene ring remains the same. Now what we have to do is we have to reduce the CHO group. The number of carbon atoms should not change. The CHO group, aldehyde, when reduced, gets converted into an alcohol, right? So this is benzyl alcohol. In the common system, I would call it as benzyl alcohol. And here the product is sodium salt of benzoic acid. Or you could also say sodium benzoate. Right? Have you understood the difference between the first product that you formed and the second product? So this was your original product, which I mentioned that this is wrong. Understand over here that here it is the side chain which is getting reduced. Whereas here you are forming a completely aromatic alcohol which is actually phenol. The OH getting attached to the benzene ring. The properties of these two compounds are very, very different. This will behave like an aromatic alcohol, whereas this compound will show you more properties of aliphatic alcohols because your OH is not attached directly to the ring. It is attached to the CH2 group. I would now like you to pay attention to what change is being undergone by carbon. So I've calculated the oxidation state of carbon like a normal student would. I have not memorized it. So here, let's say the oxidation state of carbon is X. We know that hydrogen is +1 and oxygen is -2. So the entire oxidation state, the sum of the oxidation states of all these should be 0. So X of carbon -2 of oxygen plus 2 times of 1 should be equal to 0, right? That's the same calculation I have shown over here. So in other words, the oxidation state of carbon that I get over here is 0, right? The oxidation state of the carbon atom here is 0. Now go ahead and give me the oxidation state of carbon in CH3OH and HC double bond OOH. Same logic, the oxidation state of oxygen is -2, oxidation state of hydrogen is +1. The sum of the oxidation states, because these are all both neutral molecules, the sum of the oxidation states would be 0. Try doing it. Yes, I have drawn the structures down also. You can have a look, try calculating. I hope you know how to determine oxidation states. If not, then there is a separate video which covers oxidation states and balancing ionic equations. Although we don't require it for this reaction, but balancing of ionic equations by both methods is also covered on the channel. So have you calculated? I've got the oxidation state of carbon in. Now, if you see the condensed form is CH3OH and here the condensed form is HCOOH. Yes, you can also calculate it as HCOO negative and A positive. You can also calculate the oxidation state of carbon with the ion as the complete molecule, with the taking into consideration the ion instead of a molecule. I found this easier to explain, that is why I have taken this as an example. Only thing is, in that case you would get the total charge on the ion as -1. So the oxidation state of carbon in the case of methanoic acid, so this one is methanol and I have methanoic acid. So let's jot it down: methanol, methanoic acid. So what do the oxidation states come out to? Okay, this is -2 and this one is +2. I hope we've all got it right. Now look here very carefully. What has happened here is carbon has changed from an oxidation state of 0 to -2. Oxidation state has become less, it has reduced. In other words, this is an example of carbon getting reduced. Look at the second one. The oxidation state of carbon has changed from 0 to +2. In other words, it has increased. The oxidation state has increased. That means it's an example of oxidation. When we are talking about Cannizaro's reaction, HCHO plus NaOH getting converted into CH3OH and HCOONA. In the first case, HCHO is getting reduced. At the same time, the HCHO, so if you remember, we had put it as 2 molecules in the balanced chemical equation, right? The second molecule, on the other hand, is getting oxidized. What do you call these reactions as where oxidation and reduction is taking place simultaneously. Yes, they are called as redox reactions. Easy? Right? Here our methanol is undergoing a reduction as well as oxidation at the same time. When there is a change in oxidation state of the same molecule happening within a reaction, there's a specific name given to that, and it is called as the disproportionation reaction. That is a reaction in which a compound gets converted to next higher degree of oxidation and the next higher degree of reduction. In other words, it's undergoing self-oxidation and reduction. You would have done examples of disproportionation reaction in inorganic chemistry as well. Can you recall any of them? Remember the topic of phosphorus, compounds of phosphorus? So that's a hint to you. Look out for disproportionation reaction. So Cannizaro's reaction is an example of disproportionation reaction. The same molecule getting reduced as well as oxidized, the same compound. What about aldehydes containing alpha hydrogen atom in the presence of concentrated alkali? Yes, they simply convert themselves into brown resinous products, which is a result of successive addition. We are not going to talk about this in greater detail, and we shall move on to the next reaction called as the Teschenko reaction. It's nothing but an extension of Cannizaro's reaction. So it's an extension of Cannizaro's reaction. Only thing is, this reaction is shown by all aldehydes, whether they have alpha hydrogen or do not have alpha hydrogen atom. That means all aldehydes, but our catalyst or the reaction medium is going to change. We are taking aluminium alkoxide. Alkoxide comes from alcohol. So alcohol, the ion formed from it is alkoxide. The alkoxide forming a compound with aluminium valency 3. So you will have the formula RO whole thrice Al. Remember writing of the chemical formula? It comes in handy here as well. So in the presence of aluminium alkoxide, the aldehydes get converted into alcohol and carboxylic acid. Notice here the aluminium alkoxide is only acting as a catalyst to bring about disproportionation. But you remember the reaction of esterification. What is esterification? The combination of an alcohol and a carboxylic acid to give you an ester. So they condense. Condense means it has to lose some molecule. And what is that molecule it is going to lose? It is going to lose a water molecule. Hence, esterification takes place and we get ester as the final product. Now your chance to write the reaction. So we've taken an example of ethanol over here in the presence of aluminium ethoxide, because you see C2H5OH, that's ethanol. Remove the hydrogen, ethoxide, right? What will be the products formed? Give it a try. Pause the video, write the products yourself. It will do you good to try. You can always scroll ahead, nobody can stop you. But when you are coming to learn over here, why not learn it with a little bit of honesty? Okay, you wrote? Oh, well done. So here the product, so let me break it down, CH3CH2OH, and the next higher degree of oxidation is CH3COOH, and when they will condense H2O, make sure that you get the reaction, the product CH3. I prefer to write it from the carboxylic acid end, CH3COO, CH2, CH3. 2 carbon atoms over here, ethyl, 1 and 2 carbon atoms over here, so ethanoate, right? And we form an ester as the final product. Don't forget that this is taking place in the presence of aluminium alkoxide, and the name of this reaction is Teschenko reaction. Interestingly, this may not be a part of some of the curriculums, so you may choose to ignore it. You may, go ahead to the next slide. Other than Tollens reagent, Fehling solution test, there's another interesting test to distinguish between aldehydes and ketones, and it's the test with Schiff's reagent. Now I've tried to draw it as as colorful as possible so that it's easier for you to remember. Aldehydes, when added to Schiff's reagent, immediately turn it into a pink color. We say that the pink color is restored. Why do we say that the pink color is restored? Because our original solution is actually pink color, but we decolorize it by passing sulfur dioxide to give us Schiff's reagent. So Schiff's reagent is originally colorless. As soon as you add an aldehyde to it, it turns pink in color. Interestingly, the ketones do not restore the pink color. That is how we can distinguish between aldehydes and ketones. So let's write it down in the title as well. Now the question arises, what is Schiff's reagent? Schiff's reagent is nothing but rosanilin hydrochloride. Aniline, it's a derivative of the nitrogen compounds, right? Hydrochloride dissolved in water and then decolorized by passing sulfur dioxide. That is what I mentioned here, that the Schiff's reagent is originally pink color, but then, not the Schiff's reagent, original compound is pink color when you dissolve it in water and you decolorize it by passing sulfur dioxide. As soon as you add the aldehyde, the pink color gets back. So that helps us to identify aldehydes. You are not required to know the formula or the structure or the reaction mechanism details. Yes, I like that smile on your face. Now that brings you to this part 2 of the properties of aldehydes and ketones, the part 2 of the flowchart on aldehydes and ketones, which we have been covering over the past 2-3 videos. So we spoke about aldol condensation, we spoke about crossed aldol condensation, we spoke about Cannizaro's reaction today. We also spoke about the Schiff's reagent test and the Teschenko reaction. And this flowchart best done or best made use of when you draw it yourself. When you draw it yourself, so many things will get embedded in your mind. Now, if you remember, I'd given you this chart, right, where we had listed the properties part 1. Yes, for those of you who are new to the channel, you must be wondering what we are talking about. You'll find lovely, very, very helpful flow charts on the channel. And when I'm saying very helpful, I'm not boasting about what we do. It is a review by students. It's the interest expressed by the students who found these charts very, very helpful to have a bird's eye view of the topic. So we have aldehydes and ketones properties. So left side we've done nucleophilic addition, right side we've got nucleophilic addition followed by elimination. You will find all these flow charts on the website, on the site Pen and Paper Chemistry. Just Google it and you will find it. It's a Google site. And then what we had done was we had added part 1 to this and we had added part 2 to this, right? As we keep doing, we keep adding the flow charts. And since today we've already completed the aldehydes and ketones set 2 of the properties, let me replace these with the entire flowchart of the properties of aldehydes and ketones. So we have the properties part 2 flowchart all compiled beautifully. I'm actually smiling at the amount of learning we have done together and we will continue to do together. You can take screenshots of these flowcharts, but better to draw it yourself. If you are confused, you will also find, as I said, these flowcharts on Pen and Paper Chemistry. Not just flowcharts, there are a lot of notes and helpful material that you will find on the chart, on the site, sorry. And this is part 1. Polymerization of aldehydes and ketones I have dealt with separately under the topic of polymerization or polymers. There's a separate playlist on polymerization wherein we have dealt with the different types of polymerization, polymers, types of polymerization, step chain, chain growth, all terms taken in detail on the channel. So I would request you to refer to that in order to study the topic of polymers of aldehydes and ketones. Please keep the feedback coming. It motivates me to keep going on. Thank you so much for being together. See you in the next video.